So thanks, Kosuke, for agreeing to join us for the quantum machine learning journey of cloud security. And in the past, we had like many speakers from different places talking about quantum machine learning. And this time we have Kosuke from Japan, Osaka University. And he will talk about near-term quantum machine learning techniques. He has made many fundamental contributions to the area of NISQ and machine learning, including the quantum circuit learning paper, which is like quite a decent paper. And yeah, I mean, one of the works which I particularly like from Kosuke is his work about removing the need of Hadamard test in certain scenarios, which was also like a talk at Acquis. So we gave the talk, and after I think your talk, like a couple of sessions, it was my talk. So I remember from Acquis 2019, like I think you were there, and there was this talk on Hadamard tests. So yeah, I mean, quite excited to have you here, and please start.
Okay, thanks for the introduction, and thanks for inviting me to talk about my work at this meeting. And yeah, so yes. So I'm going to talk about near-term quantum machine learning techniques in this talk, and I am Kosuke Mitarai from Osaka University, and I'm also a member of QNASYS, which is a Japanese quantum software company. So yeah, let me start. So as you all know, as you may all know, NISQ devices are like booming around, and the NISQ devices are something like has something like 50 to 100 qubits, and but the depth of the circuit is limited to some hundred of gates or something. And so what I'm talking about, what I'm going to talk about is how can we utilize this their potential computational power for like practical applications like machine learning. So and main concept around the NISQ device is the variational quantum algorithms, where we use a parameterized quantum circuit, use theta on the quantum computer, and we calculate the cost, some kind of cost function on the quantum computer, and then we run optimizer on maybe a laptop or your classical computer to like update this parameter theta to like optimize this cost function. So yeah, this variational quantum algorithm uses very effectively the shallow quantum circuit by like tuning the circuit to complete some specific task. And a very famous example of VQA is the variational quantum eigensolver, as you all may know. And but yeah, I will just talk about it a little bit. And this VQA is an algorithm for searching ground state of a quantum system. And so this works for a Hamiltonian, which can represent some molecule or something. And then yeah, we run something like this. We run the quantum circuit U theta and measure some observable. And on classical computer, we compute the average or expectation value of the Hamiltonian, and we want to minimize this energy. And so in this case, this H theta serves as a cost function, and we want to minimize this H theta by repeatedly updating theta on a quantum computer. So I will get into the main topic of this talk, and what I will present is the one that I did in like 3 years ago, and it is called quantum circuit learning. And also I would also talk about experimental work on quantum quantum machine learning, which we did a quantum kernel method on solid state NMR platform. And also I will talk about, if there's time, I will talk about quantum recurrent neural network, which we kind of just posted on the archive on last December. So first, I will talk about quantum circuit learning, which is an extension of the variational quantum algorithms to the machine learning tasks. So, as you, this might be too easy for you, but yeah, machine learning. In machine learning, we want to like model the input and output relation by a parameterized function from a given data set like this. So for example, you are given with the maybe handwritten digit like this, which is MNISQ data. This is taken from MNISQ data. And we want to construct a function which has parameter W1, W2, and so on. This example is made from neural network, but we want to learn or construct a function that successfully classify 0 or this is 0, this is 1, and this is 1, and this is 5, and so on. I mean, yeah, we want to construct such a function on the computer. So what we propose in this paper, which we call quantum circuit learning, is the machine learning algorithm for the NISQ devices. So this algorithm consists of the quantum circuit part and the classical computer part, as in the old variational quantum algorithms. And so in this quantum circuit learning algorithm, we first input the input data to a quantum state by some circuit UX. So we are given with some input data and teacher data. Input data is X and teacher data is Y. And we input X on a quantum state like this, and we get psi in X. And then we mix this state by another unitary V theta on the here. And we get output state psi out, which depends on the input data X and the parameters theta. And we measure this state. We measure some observable on this state and get expectation value. And then we compare this value with this teacher data. And we want to minimize the difference between this output and the teacher. So we want to minimize something like this. For example, we want to minimize the square loss. And on the classical computer, we decide which direction the theta should be updated, and we update theta and run iteratively this loop. And so if we loop through this many times, and if we achieve the convergence, we expect this quantum circuit to output something like this. So if we input X, and we can get a result which is close to the teacher. And this possible advantage of this quantum circuit learning approach is that the data is encoded into a 2 to the n dimension vector, which means 2 to the n dimensional feature. And I will just explain about what this feature mean in the next slide. So the feature map is a map that transforms data x to some other space phi x to extract pattern in the data. So maybe this example is the maybe most used to explain what feature map is. So in this example, we have circle-like data on a two-dimensional plane. And we want to classify these blue dots and the red dots by some linear model, but in this case, any writing any line cannot separate correctly the blue dots and the red dots. So in this case, linear model fails. But if we add third dimension like this, we can, because this is a circle-like data, we can add the third dimension to be x1 squared plus x2 squared, so that the red dots and the blue dots can be separated by a plane. And a plane is a linear model. So in this case, a linear model succeeds. So going up to a higher dimension by a feature map, you can correctly separate the two models, the two data set by like linear model. So, and going up to high dimension, sometimes makes it easy for algorithm to learn about this data set. So yeah, so like this we can gain an advantage from using the quantum circuits. So in quantum circuit learning, we map some input to the exponentially large feature space by this UX. It's QCL advantage, but future direct. This is not. Maybe this is not really required by a real world data. So future directions would be: do we really need such an exponentially large space for like real world problems like MNIST handwritten digits, like or maybe a cipher 10 data set or something? But we do not know if this helps in such a data. So this problem, I think this problem is still open and should be explored in the near future to show if the quantum machine learning is really useful in the classical setting. So this is an overview of the quantum circuit learning, and I will go into more detail into the QCL. So one thing to discuss is how expressive is the QCL. So in neural networks, there is a theorem called the universal approximation theorem, which states that any function can be approximated by a sufficiently large neural network. And I just put the picture from the textbook where this universality is shown for the neural network. So the neural network can approximate like x squared function and sine function, and maybe absolute value of x and a step function too. So important question to ask is how QCL can, if this QCL approach can achieve this kind of universality. So if we we're gonna think about this expressiveness of QCL in the 2-qubit example. So let us consider this kind of circuit where we input a data X into a quantum state by this kind of rotation gate. So if you apply this rotation gate, this will produce a state like this. This row in will be something like this. So I will use a density matrix notation because the output is linear in the density matrix rotation. So if we use a state vector notation, it will be kind of complicated because in state vector notation, the output will be nonlinear to the element of the vector. But if you use density matrix, that would not happen. And so this density matrix can be written like this, which is a product of these two operator, and this has x1 plus square root of 1 minus x squared. And if you combine them by a tensor product, there will be terms like x squared or x times square root x 1 minus x squared. So, and if we let this kind of all of these functions that appears when you take the tensor product of this input state as this function set of function gix after this u theta, and we measure some observable b at the output, this expectation value of b can be written as a linear combination of these functions, right? Because this u theta is a linear transformation of on the density matrix too. So yes, the output is linear combination functions. So to answer the question, let me consider the n qubit case where we use the same kind of input gate like this, RY rotation by arcsine x. The set of function at the input will be something like this: 1 and x and square root 1 minus x squared to the n, right? This set of function is created by the tensor product structure of the quantum states. And the output b, expectation value b, will be in the form of some of this, same as in the previous slide, but this has the this is a term like x and x squared and x cubed and all the way up to x to the n. So with if we can use fully controlled, what I mean by fully controlled is if we can use like any unitary on the n qubits, approximation of arbitrarily analytical function is potentially possible because we have 1 and x squared and x cubed and to the x to the n. So yeah, so this I was just skip this half of the slide, but so to show this universality, we conducted numerical simulations to learn these functions, where we learned the x squared and then exponential x and the sine x and this absolute value of x. So in this example, I trained the quantum circuit to output these functions by training on this teacher, and you can see that output after training really agrees with the teacher, and it is outputting various functions on the x. So, but so yes, and yeah, please see the paper for the numerical simulation details, like what quantum circuit we used and what kind of optimizers we used. So also in the quantum circuit learning paper, we propose a technique for gradient-based optimization, where maybe you guys might know about, but I will just explain for. I will just briefly explain this. So QCL was the algorithm like this, where we use parameter quantum circuit and we update this parameter theta on the classical computer. But in this updating theta, gradient-based optimizer often performs better than the gradient-free optimizer. So we propose a technique for analytical gradient calculation, and it is now called as parameter shift rule. But yeah, I think we first proposed this kind of technique. So yeah. So I will explain how we can get analytical gradient of the output. So we assume that the ansatz is structures like this, where any parameterized circuit, parameterized unitary, is generated by some Pauli operator A, and we measure some observable B. Then this assumption allows us to calculate the gradient in this way, where we measure the expectation value of B by shifting the parameter by pi over 2 and pi over 2 minus pi over 2. And then we combine them by this formula in B plus minus B minus, and then you get the gradient of the expectation value of B with respect to the case parameter. Yeah. So this is all I have for the quantum circuit learning. So yes, so in quantum circuit learning paper, we have proposed a machine learning framework using a near-term, low depth quantum computer, and yeah, it employs the exponentially large space of the quantum system, and the tensor product structure gives us nonlinearity and even the universality in some sense. And we also propose gradient-based learning on for variational quantum algorithms in general, maybe. So, are there any questions to this point?
Are there any questions from audience? Seems there was no more question, because I think people are probably well aware with your quantum circuit learning paper. So I think,
okay.
Yeah. So yeah, but one thing about this, the stuff about when we talk about which feature maps are important feature maps, they are often used to construct kernels also, right? You can construct the appropriate kernels, and then so in the paper by Adam Harrow and then by Maria Schuld, they talk about these things, and one of the open question is there that what kind of kernels, feature maps we should have, such that we can, which is quantumly easy to calculate but classically difficult to calculate, but at the same time it gives you relevant information. It just does not calculate anything, but calculates something useful, so. And we know that the current quantum computers are noisy. So let's say if you have some kind of a noisy feature map, do you have any intuition of whether we can get some kind of quantum advantage, and what kind of feature maps will be a good feature map?
Yeah, that's a good question, and I don't really have an answer right now. But yeah, this might be something that everyone's saying about quantum machine learning, but yeah, we should use some quantum data to gain a quantum advantage on quantum machine learning. Yes, and yeah, we and at our group we are also doing something like that. We are using the VQA solution to learn the phase transition on the quantum computer, and that kind of approach can be, can gain a quantum advantage because classical computer cannot even hold a general quantum state. So yeah, I don't know how we can construct this feature map for the classical machine learning task.
May I add a comment here?
Yeah, sure.
Hi, Kosuke. This is
Hi.
José Ignacio Latorre. Yeah, building on your paper, we wrote a paper that was published now in January that we saw that to have this universal approximation, you can prove a theorem, and the theorem only needs one qubit to show that you have a universal approximation. And actually, the trick is that rather than having this X input in the first stage, you simply re-upload it subsequently. And then the mapping is you map that structure to a Fourier series, which is then a universal approximation by construction of theorems that we have in the past. And you can even make a one-to-one map to a neural network with an intermediate neurons. So really, this is clear now, and the next step is to understand why 2 qubits, so entanglement, goes beyond that. But at least this is a systematic way to understand why it's better, why a quantum circuit might be better than neural networks. So, okay, and we have a hint why several qubits improve over the universal approximation of one.
That's true.
But you can do that little by little. I think we will understand that.
Yeah, that's true.
Yeah, thanks a lot for the comment.
Yeah, thanks for the comment.
So, are there any questions from the audience? Yeah, I mean, like, if you have any question, please ask, because I mean, Kosuke was the first guy to propose like how to do machine learning with the variational circuits, and if you have something that you have been thinking about, like, it's a journal, so without hesitation, just ask him. Okay, I mean, maybe towards the end or something like that, we'll ask. Or
well, let me then ask on the derivative, on the gradient. Why do you need 2, and why don't you take the analytical derivative on the gate? That's enough. Why do you have to run twice and combine?
Okay, that's true. And yes, so one way of doing the analytical gradient is just taking derivative of this circuit, and where which produces A here, and I mean taking derivative of this circuit with respect to theta k will produce A in the circuit, but to use it on expectation values, the expectation value is defined as I don't have this equation, but expectation value is defined as the u b u dagger, right? U b u dagger times the input state. So taking the derivative of this expectation value will produce differentiated u b u dagger, and then the input state, and plus u b differentiated U dagger in the row in the input state. So that kind of observables are kind of hard to measure on the NISQ devices. So you can do it in principle because it is just an inner product between the states. So that's that you can do it in principle, but this is more easier for the NISQ devices. So yes, that's why we propose this kind of circuit to measure the gradient. Does it make sense?
I'll have to check the paper to understand better.
Okay, sorry about this. Okay.
I think at some point, like probably Marco Cerezo, like he proposed higher order versions of this thing, like this kind of gradient calculation, like how to calculate it. Like successively, if you apply, you will get like Hessians and like higher order functions.
Mm-hmm.
Yeah, I mean, just as a comment, like I mentioned,
Yeah.
So, yeah, I mean, thanks. Yeah, so like maybe we can proceed with the next part. Yeah.
Okay. So another work I will talk about today is the experimental realization of the quantum machine learning. I don't know the audience of this talk, but are there any experimentalists or are they all theorists?
I mean, at times we have experimentalists also. I don't know whether today we have, but
Okay.
expect that probabilistically there might be some. Yeah.
Well, so yeah, I will talk about the experiments on this quantum machine learning techniques. So what we use in this experiment is NMR. And so NMR is a technique that controls nucleus spins in a molecule. So the advantage of the NMR is this is really an old technique which originates in like 1960 or something. So these control techniques are really sophisticated and high. The control can be done really high fidelity, and also there's so many molecules in there, so you can get the expectation value by one shot. And also, disadvantage of the NMR is the difficulty in the initialization of qubits, and because of the very low frequency of the spins. But yeah, let me explain how the NMR works. So we have a superconducting magnet which is like 2 meters tall or something. And we apply static magnetic field here. We have static magnetic field here by this superconducting magnet. And in here we have a coil, and we introduce the RF current here, and it will introduce the RF magnetic field in this coil. And in here there's a sample, and this molecule is called adamantane, and we use this molecule in our experiment too. But there is so usually the molecule here is the organic molecule, which consists of C and H, and this hydrogen atom has a spin half. So we control the spins, hydrogen atom or hydrogen nuclear, which is just a proton. So we control a proton spin on the by the arc current on the produced by this arc spectrometer. Yes, so this is how this NMR works, and we use this for quantum machine learning applications. So in solid state NMR, the initial state, so I will explain about the dynamics of the NMR. So the initial state will be something like this, with this epsilon is approximately 10 to the minus 5, which is really low. And this is the disadvantage of the initialization. This is the initialization problem in the NMR experiments. So it is not totally initialized to 0, but it is slightly initialized in 0 direction. And the time evolution of the solid state NMR is governed by the XYZ rotations by the RF fields and the dipolar interaction between the spins. So dipolar Hamiltonian is something like this: 2ZZ minus XX minus XX, or X minus YY.
I have a very basic question, very trivial kind of. So basically, this I is the identity matrix, right? So so basically, the initial state in NMR is some kind of a maximally mixed state. Like,
yes, very close to maximally mixed state, but slightly
away because
slightly initialized.
Okay, and
yes.
So you have to and can't you okay, so you're saying that it's very difficult to create pure states with NMR device.
What did you say? I didn't get.
I'm saying pure state, not mixed state, but pure state. Suppose I want to initialize pure state, it will be difficult with NMR device.
Yes, that will be really difficult. That is why the NMR is not used as a quantum computing platform anymore.
I see.
But I think maybe 20 years ago or 30 years ago, this NMR is a very popular candidate for the quantum computing, but it is no more because of this initialization problem. But
you can apply unitaries, right? And you can always apply unitaries. And
yes. The control in the NMR is very sophisticated, and you can do. I think you can do basically anything on the NMR. So this initialization problem is just the only problem, but this is really hard to solve. And yes, for this time evolution, and by this time evolution, you can observe very complex phenomena in spin system. So there is a paper on Science which observed the dynamical phase transition in this solid state NMR, and also there is work on the discrete time crystal in Nature. So this platform is really suited for exploring many body dynamics of spin systems. And yeah, I forgot to talk about this measurement part, but in NMR measurement, we can, well, kind of not, but we can only measure the expectation value of the Z operator. But of course, you can apply these XYZ rotations to change the basis of the measurement, and also you can tune the transform this Hamiltonian into maybe C naught or something to change the basis into ZZ or XX or something. So So this is the basics of the NMR experiment, and I will use this for the machine learning. And to let you know what can be done on NMR, I will briefly explain this science paper where they observed the dynamical phase transition. So what they did is applying this XYZ rotations and using this dipole interaction, which is present like natively present on the spin system, and they created the Hamiltonian like this XX minus YY type interaction, and they observe the dynamics under this Hamiltonian, and they observe the over 100 spins can be correlated in solid state adamantine. So this adamantine in the solid state is just the ensemble of this molecules. This kind of molecule has really complex dynamics, like having like 100 spins correlated in the dynamics. So I will use this molecule in this experiment too. So turning into the theoretical side of this work, I will briefly let you remember about the feature map. And the feature map was the transform which puts data into a extract which transforms the data to like extract pattern in the data. So yeah, like this kind of thing was called feature map. And learning linear models. To learn the linear models, we can use the Kernel function, which is an inner product between the data set. So Kernel function is an inner product which measures the distance between the points. So yeah, in this example, the Kernel function in the original data is something like this, and the Kernel function in the transformed like feature space data set is defined like this. And linear models can be learned by only using the gram matrix, which is defined as the this K matrix, which has the value of Kernel functions for each pair of the training data. So for example, in linear regression, you can, in linear regression, so you have the training data sets xi and yi, and the task is to predict y for unknown x. To do this, in linear regression, you model this input and output relation by this linear function f, and we optimize this f with respect to this cost function. And the solution will be something like this. The solution can be written like this, which is made of the inverse of the gram matrix in the teacher data and the Kernel function evaluated with all the data and the unknown data. So yeah, so quantum kernel method is a method that uses the quantum computer only to calculate this gram matrix. So in quantum machine learning, we use the quantum state as feature data, and we mapped the original data into high dimensional quantum state. And yeah. So in this case, the kernel becomes the inner product between the states. And so you can compute this inner product between the all pairs of training data on the quantum devices and do everything else on the quantum computer, like calculating this, calculating the inverse of the gram matrix. So this is proposed in these papers, and it is really applicable to the NISQ devices because computing this inner product is kind of easy on even on the NISQ devices. So to implement this quantum kernel method on an NMR platform, we consider what feature map NMR can produce, because we don't have this initial zero in the NMR experiment. So yeah, so we try to map this original data into a quantum state, and it is a quantum feature. But in NMR, the initial state 0 is not like available here. So this is really a mixed, almost maximally mixed state. And this pure state formalism cannot be applied. So we modify this framework to the mixed state. And we input the density matrix rho 0.
Sorry, like I have one small question.
Yes.
Yeah. So basically, like I mean, in NMR you have this mixed state, maximally mixed state, plus this epsilon part.
Yes. Yes.
Which is a bit of like purity you can think of.
Mm-hmm.
So I mean, is it so basically whatever computation we do, is it with respect to that extra pure part that we have?
Yes. Yes.
Okay.
That's true.
And we want to like kind of amplify that weak signal kind of thing that we have. Like, is it what we do?
Okay. Signals are not weak because we have so many molecules in this sample.
Mm-hmm.
I can.
I mean by signal, I mean this epsilon. So like I mean epsilon is 10 to the power -5, right?
Yes,
so,
yes, true.
But it's very small, like compared to the other term, like the maximally mixed state. And we are doing the computation on something which is very weak. I mean, so our goal is to somehow get as much as possible from this small value of epsilon. I mean, this is my question. Is it the case?
Yes, that's the case. Yeah, that's true.
And you know already like what is the value of epsilon you have in your particular experimental setup.
Okay. Let me go further, because in our experiments we don't need the exact value of epsilon. So let me go forward. So yeah. So in rho 0, so we modify the formalism to the mixed state, and we input the rho 0, and we get data-dependent density matrix rho x, right? And something like this. And in the NMR experiment, we have rho 0 equals I plus epsilon sigma z. And as in the question, this I part does not contribute to any output. So we further modify this quantum feature by something like this. So we input, we just assume the input is sigma z, so sum of the Pauli z operator, and we consider this AX operator as a quantum feature. So AX is sigma z transformed by this unitary U. So, and this is just a detail, but for this UX, we employ Hamiltonian dynamics, which in the Hamiltonian we define as a XX minus YY type interaction, which can involve like hundreds of spins. And we also have a hyperparameter of the kernel, I mean the feature map, hyperparameter of the kernel, which is time, like how long this Hamiltonian is applied to the spins. And so to compute the kernel in the NMR experiment, we use this kind of quantum circuit. We apply UX and U dagger X, and then measure, because NMR can measure this kind of observable in the experiment. So we measure this. So we input this and we measure this. So the signal is proportional to the trace of A times A. So this kind of answers the previous question, maybe. So we do not really need to know the exact value of the epsilon, but we can get the we get the signal that is proportional to the kernel. Yes, so we define this inner product in the operator space. This is right. This is an inner product in the operator space. So we define this as a kernel, and we do this experiment, and we get something this. So in our experiment, we can. So for 1D data, this kernel is equivalent to this kernel. The value of this kernel is only determined by the difference between the data. So KNMR xi xj is equal to ki minus k xi minus xj, the function of xi and minus xj. And we can plot this value of kernel from the experiment to, in this plot. So the blue line is the shortest tau, which have less decoherence, and in the long time we have more like the signal, and the intensity of the signal is kind of suppressed by the decoherence in the NMR experiments. So so we could measure this kind of kernel function on the real actual experiment, and also if we also perform the what is called the coherence analysis of this signal, we can conclude that at the largest tau that we used in the experiment, the number of spins involved in dynamics is approximately like 25. So I think this is the largest kind of experiment in the quantum machine learning, like real demonstration. So we did a proof of concept experiment for the regression of one-dimensional data and the classification of two-dimensional data. So what we did is so the result for 1D regression is like this. So the blue points are teacher data, and the green lines are trained output from the experiment. So in a short tau, the trained output is not really close to teacher, but if we increase tau long, we can get trained output is closely like approximate the teacher. Well, these fluctuations are not due to the experimental noise. So, well, we think this long tau at this long tau, this experiment is, we could obtain the better result with a long tau. And we can also plot the performance between performance with respect to the evolution time tau, and it seems to improve with longer tau. So this is the vertical axis is the mean squared error after training, and the horizontal axis is the evolution time. So 2 correspond to 120 microsecond, and so on. Yeah, it seems to improve with longer tau, and we wanted to verify this experimental result, so we formed 20 qubit simulation using the same kind of Hamiltonian and all-to-all connection, and we calculated the kernel and the same kind of kernel on the classical computer, and it kind of resembles the experimental result too. And yeah, so this is an experiment. This is a result from the simulation, and yeah, it basically performed the same kind as performs like the experimental result too. And we can also plot the performance of this one-dimensional regression. And yeah, this agrees well with the experiment. And we also performed the classification task using the kernel support vector machine. So these dots are teacher data to be classified, and we used the experimental NMR kernel to form this classification. And at this long tau, we could correctly classify all the data points. Well, this is not correctly classified, but most of the data points, and by this long tau. So to discuss the effect of the long tau, I mean the longer tau, which means that the spins involved in dynamics is more, and we observe the better performance for this longer tau. But this can be explained by the fact that with sharp kernel in general, expressiveness of the model improves, because if we use the delta function kernel, you can create the function like this, where this model predicts the same value as the input, I mean the training data at the point where the training data was given, but at the other point, this f becomes 0, and any elsewhere than the point where the training data was provided to in the training phase, I mean. So yeah, so in the short tau, we have a wider kind of kernel, but in the long tau, we have the sharp kernel. So as tau gets longer, this kernel gets sharper and sharper, and we think that this improves the performance of the learning process. So to summarize this experimental work, so we successfully implemented the quantum kernel method using a solid state NMR, and we utilized this kind of kernel where we map the summation z operator to a feature vector in operator space, and we use the inner product between the operator and as a kernel. And I think this experiment is the first experimental demonstration of quantum kernel trick, and there has been different other experimental works which did this kind of quantum kernel methods, but their feature space dimension, they have used like 2 qubits or 4 qubits or something like that, and their feature space dimension was less than number of data, and where our approach, our work has used like 25 spins in the dynamics, and so the feature space dimension is so much larger than the number of data. So this is, I think, the first demonstration of a quantum kernel trick, where this kernel method is does reduces computational cost. Yes, so this is a summary of the second one, and I think I will skip the third one because I'm running out of time, and yeah, so I will just close this talk at this point.
Yeah. So thanks, Kosuke. I mean, this was like a very pedagogical talk, and I believe most people followed. So at this point, if you have any question, please unmute yourself and directly ask Kosuke. Yeah, so seems there are no more questions. So, okay, so Kosuke, I mean, like if I gather, basically you're saying that with respect to quantum machine learning, the largest demonstration which has been there, which is like your experiment with 25 qubits, and because number of qubits is large, basically that makes the feature dimension like much higher than the number of data sets. Okay. Juni is asking, what is the benefit of having better initialization for the NMR experiment?
Okay. So let me think. So in this experiment in particular, I don't think there is so it's like I don't think there is so much merit in initializing the spins, because we are using the operator space of formalism, and we could get a decent result in this example. But in general, if we can initialize the NMR spins, the intensity of the signal is greatly enhanced. So if we can, if we can improve this epsilon by like 100, by a factor of 100 or maybe like 1,000, that will improve the signal to noise ratio by the same amount. So that will be the main contribution in this framework. But to apply this NMR to like general quantum computing, initialization is crucial, because you have to start from the 0 state. So I think this answers the question.
Yeah. Okay. Are there any more questions from anybody else from the audience? Oh, Juni is asking, he's saying, do you need to be able to tune the dipolar interactions?
In this experiment, no, because I mean, if you can tune this interaction coefficient, the kernel will be different, and the kernel, I mean, I mean, that can serve as a hyperparameter of the kernel, but in this experiment, we didn't really change this coefficients Dij in the experiment, and we just changed the form of the interaction into from zi to zi to zz minus xx minus yy form to the xx minus yy form. So in this experiment, no, but it would be really interesting to change the coupling between the spins. And I don't know if you can even do that because in NMR we can like in particular for the solid state NMR, you can't really access to the individual qubits because their frequencies are really degenerate because they have really symmetries. So I don't think you can even do that on this solid state NMR experiment, but I think you can do that in like liquid state NMR or other experimental platforms. So yeah, I think that is the case.
Okay. Are there any questions from audience? Okay. I think Juni is asking another thing. He's saying, interesting. So
Okay.
not having individual control is not always an issue.
Yeah. So yes, because in this quantum kernel method, only thing you have to do is to implement some circuit like this. So if you have technique to like invert the dynamics in the first part to create this U-dagger part, that would be enough to execute this quantum kernel methods. But yeah, in general, quantum machine learning tasks like quantum circuit learning, we will need to address the individual spins to like to maybe parameterize the circuit or something. So yes, that's true. I'm reading the chat from Juni, and yeah, I think that's true that if you can hyperpolarize nuclear spins, that would be really interesting to explore.